There is a point in space so far from Earth that the light arriving from it today began its journey before the dinosaurs existed. Before the oceans finished forming, before nearly every species alive on this planet drew its first breath. That light has been travelling for so long that entire geological eras passed while it crossed the darkness between us. And when astronomers finally collected that ancient light, when they pointed instruments toward that particular corner of the sky and began analysing what they had found, the numbers that emerged did not fit comfortably inside ordinary scientific language. They did not fit comfortably inside ordinary human imagination either. What they discovered was not simply large. It was not simply old. It was something that forced serious researchers to sit quietly with their calculations and ask whether the universe itself was operating by rules. Nobody had fully written down yet. The object is called T-on 618. That name sounds procedural, catalogue language. A number assigned to a point of light in a survey conducted decades ago. And for a long time, that is essentially all it was. A data point, a faint smear on photographic plates, unremarkable in appearance. The universe contains approximately 2 trillion galaxies, and astronomers have catalogued millions of individual objects inside those galaxies. Most receive numbers rather than names because there are simply too many to name otherwise. TON 618 received its number in 1957. A routine survey. No particular excitement. What nobody understood at that moment was what the number had been assigned to. It would take decades before the instruments existed to look carefully enough. And when they finally did, the casual bureaucratic name suddenly felt deeply insufficient. TON 618 is classified today as a quasar. That word requires a moment of attention because most people have heard it without fully understanding what it means. And the reason most people have heard it without fully understanding what it means is that what it actually means is genuinely difficult for the human mind to hold. A quasar is not simply a bright object in space. It is not a star. It is not a galaxy in the conventional sense. It is something more fundamental and more violent than either of those things. A quasar is what happens when a supermassive black hole at the center of a young galaxy begins consuming matter at a rate so extreme that the surrounding region becomes the brightest continuous object in the known universe. Let that settle for a moment. Not a bright star, not an exploding star, not even a galaxy, a single region of space surrounding a single object, brighter than everything else. To understand why TON 618 disturbs researchers in ways that extend well beyond its classification as a quasar, it helps to first understand what a quasar actually produces and what has to exist at its center for that production to occur. When matter falls toward a black hole, it does not fall cleanly. It spirals. It collects into what is called an accretion disk, a vast rotating structure of superheated gas, plasma, and infalling material. As that material accelerates and compresses, temperatures rise to levels that make the surface of ordinary stars feel mild by comparison. The friction, the radiation, the electromagnetic forces operating within that structure. They all combine to produce light output so extreme that a single quasar can outshine an entire galaxy of 100 billion stars, an entire galaxy. 100 billion individual suns, and a quasar can exceed that combined output many thousands of times over. The most powerful quasars ever detected exceed the luminosity of an average galaxy by factors approaching 10,000. A single point of space outshining 10,000 entire galaxies simultaneously. I want you to sit with that image for a moment before we continue. Because it is not a metaphor, it is not an approximation. It is a measured, verified, documented physical reality about the universe you currently inhabit. Toon 6A18 is among the most luminous quasars ever recorded. Its apparent brightness from Earth is faint, only because of distance. The object sits approximately 10.5 billion light-years away. That distance imposes a dimming effect on any observed brightness so severe that even something producing incomprehensible energy output becomes a faint smear, visible only through powerful telescopes. But the intrinsic luminosity, the actual energy output at the source, is approximately 140 trillion times the luminosity of the sun. 140 trillion. It is the kind of number that the human nervous system is not designed to process emotionally. Our intuitions evolved to handle distances we can walk, time scales we can live through, and quantities we can count. A number like 140 trillion simply defeats ordinary comprehension. So try this instead. If you replaced our sun with Tuon 618 at the center of the solar system, the Earth would not merely be scorched. There would be no meaningful concept of Earth remaining. The energy output would overwhelm every physical structure at interstellar distances. Nearby star systems would be bathed in radiation levels incompatible with complex chemistry. The region of influence would extend so far in every direction that it begins to lose meaning as a spatial concept. That is what sits at the center of Tuon 618. Or rather, that is what sits above it. What sits at the center is something else entirely. The black hole at the center of Tuon 618 has a measured mass of approximately 66 billion solar masses. 66 billion times the mass of the sun compressed into a single gravitational object. I have heard researchers describe this number in academic language, and I have noticed how even experienced astronomers pause slightly after saying it aloud. Not dramatically, professionally, but there is something in the pause, a hesitation that suggests the number does not quite fit inside the frameworks they were trained to use. Because there is a problem with 66 billion solar masses, a significant one. And it goes to the heart of why I said at the beginning of this that Tuon 618 may be something worse than a black hole. Modern astrophysics has a well-developed understanding of how black holes form and grow. The largest ones, the supermassive black holes that sit at the centers of galaxies, are understood to grow through two primary processes. They consume surrounding matter over time, gradually accumulating mass, and they occasionally merge with other black holes when galaxies collide, Combining their masses, these processes take enormous amounts of time, enormous even by cosmic standards. The universe is approximately 13.8 billion years old. Supermassive black holes at the centers of large nearby galaxies, objects like the one at the center of the Milky Way, have had essentially the entire current age of the universe to grow. And those objects, while genuinely massive, remain manageable within theoretical frameworks. They grew over billions of years through processes that models can track and replicate. TON 618 is observed at a distance corresponding to 10.5 billion light years. This means we are not seeing TON 618 as it exists today. We are seeing it as it existed 10.5 billion years ago, when the universe was only approximately 3 billion years old. 3 billion years. The universe had barely begun. And already, at that early moment, TON 618 contained 66 billion solar masses inside a single gravitational object. The question that follows from this is not merely academic. It is, in a genuine sense, foundational. How does something accumulate 66 billion solar masses in only 3 billion years? The answer, according to current models, is that it almost cannot. There are physical limits on how quickly a black hole can grow. As a black hole consumes matter, the radiation pressure from the surrounding accretion disk begins to push infalling material away. This creates a natural speed limit on consumption, a ceiling on how rapidly mass can be added at any given time. The theoretical maximum accretion rate has a name. It is called the Eddington limit, and here is where things become uncomfortable. If a black hole of stellar mass, the kind that forms when a large star collapses, had begun growing at the very earliest moment the universe permitted, accreting mass at the absolute theoretical maximum rate, continuously, without interruption, from the beginning of cosmic time, until the epoch when TON 618 is observed, the resulting mass would still fall dramatically short of 66 billion solar masses. The math does not work. The timeline is too short. The known processes are too slow. The physical constraints are too limiting. And yet the object exists. TON 618 is not a theoretical prediction. It is not a projection from incomplete data. It is a measured object. Its mass has been determined through multiple independent methods. Its distance has been confirmed. Its luminosity has been verified. The universe produced something that the universe, according to our best understanding, should not have been able to produce in the time available. This is where the title of this script requires honest examination. 618 is literally not a black hole. It almost certainly is a black hole in the technical gravitational sense. Matter falling toward it would cross a genuine event horizon. Information would be lost. The singularity physics would apply. But when I say it may be something worse, I mean something more specific. I mean that TON 618 may represent a category of object that our current physics has not properly described. Something for which the label black hole exists as a placeholder, a name attached to a phenomenon whose true nature remains genuinely unclear. And the unsettling part is that the more carefully researchers examine objects like Tion 618, the more the standard black hole model appears to strain under the weight of what it is being asked to explain. Let us talk about what sits inside a black hole, or rather, let us talk about what is supposed to sit inside one. In the standard model of general relativity, every black hole contains a singularity, a point of infinite density, a location where the equations of physics stop producing meaningful numbers and simply produce infinities. In mathematics, an infinity appearing in your calculation is often a signal. Not that the universe actually contains infinity at that location, but that your model has broken down, that you have reached the edge of what your framework can describe. Physicists have understood this for decades. The singularity inside a black hole is not thought to be a real physical thing in the way that a planet or a neutron star is a real physical thing. It is understood to be a mathematical artifact indicating that general relativity has reached its limits. What actually happens at the center of a black hole, what the correct physics would describe if we had that physics, remains entirely unknown. This is not a minor footnote. This is perhaps the most significant gap in fundamental physics currently facing the field. Every black hole in the universe contains at its center a region that modern science cannot describe. For an ordinary stellar black hole, this might feel philosophically interesting, but practically remote. Those objects are small. Their event horizons can be measured in kilometers. The region of genuine mystery is contained inside a relatively modest gravitational object. For Tion 618, the scale of the unknown changes entirely. The event horizon of Tion 618, the boundary beyond which nothing returns, is so large that it would comfortably contain our solar system many times over. Place our entire solar system, the Sun, all 8 planets, Pluto, the Kuiper Belt, the scattered disk of debris extending billions of kilometers from the Sun. Place all of that inside the event horizon of Tion 618, and it would be swallowed with room remaining. The region of genuine physical mystery, the place where our equations break down and we simply do not know what exists, is larger than our home solar system. Whatever is at the center of Tion 618 is not just unknown. It is unknown at a scale that exceeds ordinary human spatial reference entirely. There is a concept in physics called an ultra-compact object. This is a term used, sometimes quietly, sometimes somewhat cautiously, to describe objects that behave like black holes from the outside, objects that have event horizons, that warp space-time in the expected ways, that absorb matter and produce the expected electromagnetic signatures, but that may not contain a traditional singularity inside. These are theoretical. No confirmed ultra-compact object has been definitively identified and distinguished from a conventional black hole. Doing so would require observational access to interior physics that current instrumentation cannot provide. But the theoretical landscape here is considerably stranger than popular discussions typically convey. Some researchers have proposed that at sufficient mass scales, the conditions inside what we call a black hole might produce something fundamentally different from what general relativity predicts, not a singularity. Something else, something for which our physics currently has no adequate description. Others have proposed structures that exist at the threshold between matter and space-time geometry itself. Objects so dense that their interior is not simply compressed matter, but something closer to a different phase of physical reality. These ideas are speculative. I want to be transparent about that. They are not established science in the way that general relativity or quantum mechanics are established science. But they emerge from serious researchers working at the frontier of theoretical physics. And they emerge, at least partly, in response to objects like Theon 618. Because Theon 618 creates a problem not just for cosmology, for physics itself. The problem has two faces. The first face is the formation problem, which I have already described. How does something this massive exist this early in cosmic history? The second face is less discussed publicly, but may be more profound. It concerns what happens to space-time itself in the vicinity of extreme mass concentration. General relativity describes gravity as the curvature of space-time. Matter curves space-time. Curved space-time directs the motion of matter. The greater the mass concentration, the greater the curvature. At sufficient mass, space-time curvature becomes so extreme that regions of space become causally disconnected from the rest of the universe. That is what an event horizon is. A boundary in space-time geometry, not a physical barrier in the conventional sense, a geometric feature of reality itself. For a black hole of 66 billion solar masses, the space-time geometry within and around the event horizon is so extreme that it qualifies, in a genuine theoretical sense, as a different region of the universe, not merely a different location, a different causal region, a place where the arrow of time points differently than it does for the matter and light outside, where the fundamental geometry of reality itself has been reorganized by mass. I want to stop here and say something that I think deserves to be said plainly. We do not know what is inside Theon 618. Not in the casual sense in which scientists sometimes say, we do not know something while having strong theoretical predictions they expect to be confirmed. We genuinely, fundamentally, with no clear roadmap toward resolution, do not know what exists inside the event horizon of Theon 618. We have no mechanism for finding out using any technology that currently exists or any technology that current physics suggests might become possible. The interior of Theon 618 is, to an unusual degree of philosophical seriousness, not part of the observable universe. Whatever exists, there will never send information to us. Nothing that enters will return. It is a permanent exclusion zone within reality itself, and it is 66 billion times the mass of our Sun. Now I want to talk about something that receives far less attention than the raw mass of Theon 618, but which I find personally more unsettling. What Theon 618 implies about the universe we cannot see. Theon 618 was discovered by survey, routine observation. A catalogue entry, one of many objects examined in a broad sweep of the sky. This matters because 2 in 618 was not found by searching specifically for the most extreme objects. It was found by looking at a patch of sky and recording what was there. And what was there happened to be among the most massive, compact objects ever detected. The universe is not small. The observable universe alone contains hundreds of billions of galaxies, and the observable universe represents only the region from which light has had time to reach us. Beyond that boundary, which is not a wall or a surface, but simply the limit of our causal horizon, the universe continues, without known boundary, possibly without limit. If T-on 618 was found essentially by accident in a routine survey, if objects of this mass are simply present in the universe and encountered without targeted search, then the question of how many objects like T-on 618 exist becomes genuinely troubling. And the question of what objects exist beyond our current observational limits, in the regions of the universe we cannot see, becomes something that sits uncomfortably between science and philosophy. There is a quiet debate within astrophysics about the distribution of ultramassive black holes across cosmic history. How common are they? How massive can they become? What is the upper limit, if any, on black hole mass in this universe? Current theory suggests that the most massive black holes should stop growing relatively early in cosmic history. The reservoir of infalling matter eventually depletes. The quasar phase ends. The black hole becomes dormant, a dark monument at the center of a galaxy that no longer feeds it. If this is correct, then the most massive black holes in the universe are not forming today. They formed long ago, during the early epochs of intense galaxy formation, and have been sitting dormant since. T-on 618, if it follows this pattern, would now be a dark object. Its quasar phase long ended. Sitting at the center of a galaxy we cannot clearly identify from this distance, no longer consuming at the ferocious rates that once made it visible. Dormant, but still present. Still 66 billion solar masses. Still a permanent architectural feature of whatever region of the universe it occupies. Still defined by an event horizon larger than our solar system. Still containing within its interior whatever physics describes for which we have no adequate language. The formal classification system that places T-on 618 in the category of quasars, and by extension places the object at its center in the category of black holes, is scientifically reasonable. It is consistent with observational evidence. It is not wrong in the conventional sense. But classification is not understanding. Giving something a category name does not mean we have comprehended what it fundamentally is. Black hole is a category name derived from mathematical models that work exceptionally well at describing the exterior behavior of these objects, the way space-time curves around them, the way matter and light behave in their vicinity, the way they radiate thermally over cosmological timescales. But those models break down at the interior. They produce infinities. They stop predicting. They hand the physicist a singularity and quietly admit that they cannot tell you what actually exists at the center. for Tion 618, this gap in understanding is not academic. The interior region of Tion 618, the region where the known physics fails, is spatially enormous by any human reference. We have a label for the outside. We have nothing for the inside. Some researchers have asked seriously whether the singularity predicted by general relativity inside black holes is physically real, or whether it is a signal that the theory requires replacement at those scales. Quantum mechanics suggests that information cannot truly be destroyed, that nothing about a physical system can be permanently and irrecoverably lost. This is called unitarity. It is one of the foundational assumptions of quantum theory. But a classical black hole destroys information. Matter falls in. The information about that matter, the precise quantum state describing every particle, is apparently lost behind the event horizon and eventually erased along with the black hole's mass through Hawking radiation. This conflict between general relativity and quantum mechanics, the information paradox, has been recognized for decades as one of the deepest unsolved problems in fundamental physics. It is not solved. Proposals exist, some mathematically elegant, some physically provocative, none with clear experimental confirmation. And every one of those proposals, in some form or another, implies that what we call a black hole is not simply a gravitational object with a singularity inside. Something more subtle is occurring. Something at the intersection of space-time geometry and quantum information. Something that current physics can gesture toward but cannot fully describe. Tion 618 at 66 billion solar masses sits at the extreme end of this unresolved territory. There is a hypothesis called the firewall. It emerged from a 2012 paper by a group of theoretical physicists and generated significant controversy within the field. The basic idea is disturbing. Standard quantum mechanics and general relativity, when applied simultaneously to the event horizon of a black hole, produce a contradiction. To preserve quantum information, the event horizon of a black hole cannot be the smooth, geometrically unremarkable boundary that general relativity predicts. It should be for a large black hole. Instead, quantum effects might concentrate enormous energy at the horizon itself, not inside the black hole at the boundary. The firewall hypothesis suggests that what a falling observer would encounter at the event horizon is not the gentle geometric transition that general relativity implies, but a wall of intense radiation, effective annihilation at the boundary. This would mean that the interior of a black hole is not simply a region of extreme curvature leading to a singularity. It might not be accessible at all. The event horizon might be the actual endpoint, not an entrance, a termination. The firewall controversy is not resolved. Physicists continue debating whether firewalls are real, whether they can be avoided through more refined quantum gravity, whether alternative descriptions of black hole interiors resolve the paradox without the need for firewalls. But the fact that this debate exists at all is telling. It means that even the basic question of what happens when you cross the event horizon of a black hole The question that sounds simple, the question that sounds like it should have a straightforward answer within known physics, remains genuinely open. For 2on 618, a black hole so large that crossing its event horizon would not initially feel like crossing into extreme curvature, where tidal forces at the horizon would be relatively mild compared to a smaller black hole. What the firewall hypothesis implies is even stranger. A boundary that might be physically violent, even though gravitationally smooth. An event horizon that might be both geometrically gentle and physically catastrophic simultaneously. A place that physics describes in mutually incompatible ways. I want to move outward for a moment from the specific strangeness of TON 618 to the broader strangeness of what objects like it suggest about the universe's fundamental architecture. We are accustomed to thinking of the universe as organized by physical laws that apply everywhere equally. The same equations, the same constants, the same behavior, regardless of location. This is called the cosmological principle, and it is one of the foundational assumptions of modern cosmology. It is almost certainly approximately correct, but approximately correct is not the same as completely correct. And the existence of objects like TON 618, objects that form faster than models expect, that concentrate mass at levels that strain theoretical descriptions, that exist in conditions where our best physical frameworks begin producing contradictions. These objects are quiet reminders that the cosmological principle is an assumption, not a proven theorem. The universe may contain regimes of physics that current models have not fully characterized, not because the models are wrong in ordinary circumstances, but because ordinary circumstances are not the only circumstances, and the extreme circumstances, the conditions inside and around objects like 2on 618, may reveal physics that the ordinary universe simply does not display. There is a long tradition in science of assuming that the laws observed in accessible conditions apply everywhere. That tradition has been productive, but it has also sometimes been wrong. Newtonian mechanics applied everywhere until relativistic conditions revealed it as an approximation. Classical physics described all behavior until quantum scales revealed it as a subset of a larger framework. General relativity describes space-time geometry correctly across a vast range of conditions, but physicists strongly suspect it is itself an approximation of a more complete theory that incorporates quantum mechanics. What that more complete theory looks like, where it differs from general relativity, and how it behaves in the extreme conditions inside objects like TON 618, remains one of the central open questions in fundamental science. TON 618 sits at the extreme end of the parameter space where those deviations from general relativity might become significant, where the classical approximation might break down, where the actual physics of whatever underlies space-time geometry might become the dominant description. We are not equipped to see inside that region, but we are increasingly aware that it exists. There is something I want to say about scale. that I think rarely gets said directly enough. Human civilization is approximately 10,000 years old. Modern science, in the rigorous experimental sense, is roughly 400 years old. Astrophysics, as a coherent discipline, is perhaps 150 years old. The tools required to detect and characterize objects like Theon 618 have existed for fewer than 60 years. Against the 10.5 billion year journey of light from Theon 618, human scientific capability is something that happened in literally the final fraction of a fraction of the last moment of that light's travel. For 10.5 billion years, that ancient light crossed the universe, and only in the most vanishingly recent moment of its journey did anything exist to receive it, analyze it, and attempt to understand what it implied. We are extraordinarily new to this. We are, in cosmic terms, infants who have just begun opening their eyes. And what we are finding, even with our extraordinarily limited observational history, is already more complex, more strange, and more resistant to simple explanation than our models initially predicted. What we will find as those tools improve, as observations extend further in time and resolution, as theoretical frameworks evolve to accommodate the anomalies already accumulating, I genuinely do not know. No one does. And I think that uncertainty, that genuine openness, deserves to be felt rather than glossed over. There is a region surrounding rotating black holes that receives almost no attention in popular science discussions. It is called the ergosphere. The name comes from the Greek word for work, and the naming is deliberate. It describes a region where the geometry of space-time has been so severely distorted by the rotation of the black hole that nothing inside it, not matter, not light, not any physical system whatsoever, can remain stationary relative to a distant observer. The black hole rotates, and it drags space-time around with it, not metaphorically, literally. The fabric of reality in the region surrounding a rotating black hole is being physically pulled in the direction of the black hole's spin. An object in the ergosphere, even one with an arbitrarily powerful engine pointed directly against the rotation, cannot remain still. Space-time itself moves faster than any conceivable thrust can compensate. This region exists outside the event horizon. It is technically possible to enter the ergosphere and exit again. But while inside it, the distortion of space-time is so extreme that the ordinary relationship between cause and effect, between motion and direction, between energy and momentum, all of these shift in ways that require the full apparatus of general relativity to describe for a black hole like Theon 618, which almost certainly rotates. The ergosphere would extend across a region of space comparable in size to the distance between the Sun and its nearest planetary neighbours. A volume of the universe where space-time itself rotates, where the geometry of reality has been reorganized by the angular momentum of 66 billion solar masses. Inside the ergosphere, something becomes theoretically possible. That sounds at first like science fiction. It is called the Penrose process. A physicist named Roger Penrose in 1971 described a mechanism by which energy could be extracted from a rotating black hole using the ergosphere. If an object enters the ergosphere and splits into two pieces, one piece falling into the black hole and one piece escaping, and if the geometry of the split is arranged correctly, the escaping piece can carry away more energy than the original object brought in. The additional energy comes from the rotational energy of the black hole itself. The black hole loses angular momentum. The escaping fragment gains more energy than was initially present. Energy extracted from the rotation of space-time geometry. This is not speculative in principle. The mathematics is rigorous. General relativity predicts it clearly. Whether it occurs in nature in ways that matter observationally is a separate question. But in principle, the ergosphere of a rotating black hole is a region where the organized rotation of space-time geometry itself can be tapped as an energy source. For Theon 618, the rotational energy stored in the angular momentum of 66 billion solar masses is a quantity that sits beyond any ordinary physical intuition. It is energy of a kind that no human technology approaches, and that nature itself accesses only through the most violent astrophysical processes. The jets produced by quasars may partly derive their energy through mechanisms related to this. An accretion disk interacting with the ergosphere of a rapidly rotating black hole diorang energy from the rotation of space-time, focusing it into relativistic beams extending for millions of light years. The ergosphere of Theon 618 may have been the engine behind jets that restructured the galaxy surrounding it. Organized geometry becoming organized energy, becoming organized destruction of surrounding galactic architecture. In September of 2015, instruments detected something genuinely new. Not a new object, not a new image, not light of any wavelength, a ripple in space-time geometry itself. Two black holes, each roughly 30 solar masses, had merged approximately 1.3 billion light years away. The merger released more energy in the gravitational waves in a fraction of a second than the entire observable universe radiates in visible light during that same interval. And the signal that arrived at Earth after travelling for over 1 billion years was a distortion in the distance between 2 points in space of approximately 1,000th the diameter of a proton. That is what humanity detected, a distortion smaller than any single atomic nucleus, present for a fraction of a second, carrying information about a cataclysm 1 billion light years away. The instruments that detected it are engineering achievements of extraordinary precision. But more important for this discussion is what gravitational wave astronomy implies for objects like Theon 618. When black holes merge, they radiate gravitational waves. The signal from two stellar mass black holes was detectable at 1.3 billion light years. Now consider the merger of two black holes comparable in mass to Theon 618, two objects of tens of billions of solar masses colliding and merging. The gravitational wave signal from such an event would not merely be detectable. It would be among the most energetic gravitational wave events the universe can produce, and we currently cannot detect it. Not because such mergers do not occur, but because the frequency of gravitational waves from such massive mergers falls below the frequency range that ground-based detectors can access. The wavelengths are too long, the oscillations too slow. The signals pass through every instrument on Earth, carrying information about some of the most violent events in cosmic history, and current technology cannot read them. There is a planned space-based gravitational wave detector called LISA, the Laser Interferometer Space Antenna. It would involve multiple spacecraft separated by millions of kilometers, forming a detector sensitive to the low-frequency gravitational waves produced by supermassive black hole mergers. If and when LISA operates, it would for the first time open a direct observational window on events involving objects in the mass range of T-on 618, mergers of galaxies, with their central black holes eventually spiraling together and colliding, produce gravitational wave signals that LISA could in principle detect across cosmological distances. The universe is full of galactic mergers. The universe is full of supermassive black holes. At some statistical rate, these mergers bring central black holes together over billions of years. When that happens, the gravitational wave signal propagates outward through space-time. Right now, at this moment, gravitational waves from supermassive black hole mergers that occurred billions of years ago are passing through Earth, through this room, through every atom of every person who will ever read or hear these words. We feel nothing. The geometry of space shifts by amounts so small that no biological sensor registers them, but the waves are present. The universe is communicating in a language that human technology has only just barely begun to learn. And Tune 6618, or its descendants, if it has merged with other black holes since the epoch we observe it, may have contributed to that background hum of gravitational radiation that currently permeates the cosmos. One of the more unsettling aspects of ultramassive black holes is something that receives almost no public attention. Spin black holes rotate. They carry angular momentum acquired from the matter that formed them and subsequently fell into them. This rotation is not incidental. It is a fundamental property of the object, alongside mass and electrical charge. But spin creates a problem that scales with mass in an uncomfortable way. For a sufficiently rapidly rotating black hole, the mathematics of general relativity predicts that the singularity changes its geometric character. Instead of a point singularity, a rotating black hole of sufficient spin is predicted to contain a ring singularity, a circle of infinite density rather than a point. And through the center of that ring, the mathematics suggests something that physicists handle very carefully. The equations of general relativity applied to the interior of a maximally rotating black hole suggest the theoretical possibility of closed time-like curves inside the event horizon. Trajectories through space-time that curve back on themselves. Paths through the geometry of reality that, if physically traversable, would constitute something resembling closed loops through time. I want to be extremely clear about what this means and does not mean. These solutions arise from the mathematics. Whether they correspond to physical reality is deeply uncertain. Most physicists believe that mechanisms exist, possibly quantum gravity effects, that prevent closed time-like curves from forming even where the mathematics suggests they might. The general expectation is that the universe enforces something like a chronology protection principle, that reality conspires to prevent the formation of genuine time loops. But the fact that the equations of our best gravitational theory produce these solutions in the interior of rotating black holes, even as a mathematical possibility that must then be argued away by invoking physics, we do not yet fully understand, is itself telling. It tells us that the interior of a rotating black hole is a region where general relativity encounters its most severe internal tensions, where the theory begins describing things that the theory itself suggests should be impossible. For Tion 618, almost certainly rotating, the interior geometry is not merely a region of unknown physics. It is a region where our best current theory produces solutions that most physicists believe cannot be physically real, for reasons that require a more complete theory to explain. The mathematics reaches inward and begins generating results that cannot be trusted, and we have no better mathematics to replace it with yet. There is a possibility that I have been building toward that. I want to state directly now. It concerns the relationship between Tion 618 and the galaxies surrounding it. The standard narrative of galaxy formation holds that galaxies form first. Stars accumulate through gravitational collapse of gas clouds. The first generation of massive stars forms and dies quickly, producing black hole remnants. Those remnants gradually accumulate mass, merge with other remnants, grow. Eventually, a supermassive black hole forms at the center of the developing galaxy. In this narrative, the galaxy comes first. The black hole grows inside it. But the timeline problem created by objects like Tion 618 forces a serious reconsideration of this sequence. If the mechanisms of standard growth, accretion from stellar remnant seeds, cannot produce 66 billion solar masses in 3 billion years, then either the growth was seeded by something much larger than a stellar remnant, or the growth happened by mechanisms that operate faster than the Eddington limit would suggest. Or the standard narrative of the relationship between galaxies and their central black holes is incomplete in ways that matter. Some researchers have proposed, only partly speculatively, that in certain early cosmic conditions, the sequence was effectively reversed, that a massive gravitational seed collapsed first, that the galaxy organized itself around the existing gravitational anomaly rather than producing the black hole through its own stellar evolution, that Tion 618's black hole may have preceded its own galaxy in any meaningful developmental sense. Not a black hole born inside a galaxy born around a black hole. That inversion of the standard sequence changes the conceptual picture considerably. a black hole as a seed around which cosmic structure organized rather than as a product of cosmic structure already organized. The black hole not as the consequence of galactic evolution, but as its cause. The gravitational anchor came first. The gas clouds fell toward it. Stars formed in those falling clouds. The galaxy built itself around the pre-existing darkness at its center. In this view, the most massive black holes in the early universe are not offspring of the first galaxies. They are the parents. The gravitational centers around which the universe first organized visible matter into the structures we now call galaxies. If this picture is correct, even partially it means that the architecture of the modern universe, the distribution of galaxies, the large-scale structure of cosmic filaments and voids and clusters traces back ultimately to the distribution of those early massive seeds. The map of the modern universe written by objects that formed before the first recognizable galaxies existed, TON 618, as not merely a black hole, but as a cosmic architect, one of the gravitational foundations upon which the visible universe was subsequently built. In 2019, humanity produced the first direct image of a black hole shadow. The object imaged was the supermassive black hole at the center of the Messier 87 galaxy, approximately 55 million light-years from Earth. The mass of that black hole is approximately 6.5 billion solar masses. Already an extraordinary object, already at the upper end of what most researchers considered likely for observed nearby black holes. The image showed a ring of bright emission surrounding a central darkness. The ring produced by infalling matter, heated to extreme temperatures. The darkness produced by the event horizon's gravitational shadow. That shadow is not the event horizon itself. It is larger, approximately 2.5 times the event horizon diameter due to the gravitational lensing of light around the black hole. But it directly reflects the size of the event horizon and by extension the mass of the object. Imaging it required linking radio telescopes across multiple continents, creating an effective telescope with a diameter comparable to Earth itself. The result was a blurred but recognizable image of a 6.5 billion solar mass black hole. Now consider imaging the shadow of TON 618. TON 618 is 10 times more massive than that object. Its event horizon is correspondingly larger. But it is also dramatically further away. The distance of 10.5 billion light-years compared to 55 million light-years represents a factor of roughly 200. The angular size of TON 618 shadow as viewed from Earth is actually smaller than what was imaged in 2019, despite the physical size being larger, because the distance effect dominates. Current instruments cannot resolve it. Future instruments, proposed arrays extending into space rather than limited to Earth's diameter, might in principle approach the resolution required, but we have never seen the shadow of TON 618. We know it exists. We know it is there. An enormous region of absolute gravitational darkness at 10.5 billion light-years, as it was 10.5 billion years ago. We have calculated its size from mass measurements. We have not seen it, and we may not see it in any meaningful sense of resolved imagery within the lifetime of anyone currently alive. There is something about that limitation that I find genuinely interesting rather than merely frustrating. The most extreme objects in the universe are not always the most visible ones. TON 618, by virtue of being among the most massive compact objects ever identified, is also among the most effectively hidden from direct visual resolution. Its extreme distance converts its extraordinary physical size into an angular size that defeats current technology. The universe scales its extremes in ways that do not accommodate human observational capacity. The most massive things are not necessarily the most accessible. The most ancient are not the most visible. The most energetic are not the most legible. TON 618 exists at the intersection of extreme mass, extreme distance, and extreme age, in a way that places it simultaneously at the center of scientific interest and at the outer edge of observational capability. Known well enough to be disturbing, not known well enough to be seen directly. Vatusian 618 does not exist in isolation. The universe contains multiple confirmed black holes in the range of tens of billions of solar masses. The central black hole of the Home 15A galaxy cluster has an estimated mass of approximately 40 billion solar masses, found much closer than TON 618, at roughly 700 million light-years. It represents a more accessible extreme example. Other galaxies host black holes estimated between 6 and 37 billion solar masses, depending on measurement method. These are not all the same kind of object in detail. They inhabit different galaxy types, different cluster environments, different epochs of cosmic history in terms of when they formed and how they grew, but they form a population. And that population, the ultramassive black holes at the extreme end of the mass distribution, represents something specific about the universe's capacity for concentrating mass. When astronomers began finding multiple objects in this mass range, the question naturally arose whether there was a physical upper limit, whether the universe had a ceiling for black hole mass, whether some process imposed a maximum mass, beyond which black holes simply could not grow. The answer, as best as current understanding can determine, is that a maximum may exist, but is poorly constrained. Theoretical arguments suggest that at sufficiently extreme masses, the feedback processes between the black hole and its host galaxy become so intense that further growth is effectively suppressed. The black hole grows large enough to heat and disperse the gas that would otherwise fuel further accretion, self-limiting. The largest black holes may have grown until their own influence prevented further growth, not stopped by anything external, stopped by the consequences of their own size. TON 618, at 66 billion solar masses, may be near that self-imposed limit for objects that grew in the kind of environment it occupied. But whether objects exist elsewhere in the unobservable universe, in different environments, formed by different mechanisms, that exceeded even this limit is genuinely unknown The observable universe shows us a sample of what exists. The full distribution across all of cosmic volume, including the regions beyond our causal horizon, remains entirely inaccessible. We may be sampling the moderate end of the true distribution without knowing it. The universe beyond the horizon may contain things that make TON 618 appear ordinary. We have no way to know, and that inability, that permanent causal limitation on human knowledge, is perhaps one of the most genuinely humbling features of our observational position. There is a concept in physics related to black holes that is rarely discussed outside technical literature, but which I find philosophically extraordinary. It is called the no-hair theorem. The theorem states that a black hole, once formed and settled, is entirely described by only three quantities: its mass, its angular momentum, and its electrical charge. Three numbers. That is all every detail of what fell into the black hole, every galaxy of stars that may have contributed to its mass, every cloud of gas, every smaller black hole that merged with it, every complex structure that crossed the event horizon across the billions of years of its growth. All of that information is irrelevant to the final description of the object. The black hole from the outside shows you only three numbers: mass, spin. Charge, everything else is lost. For TON 618, that theorem implies something that takes a moment to fully absorb. Billions of years of cosmic history fell into that object. The first generation of massive stars whose remnants may have seeded its formation, the gas clouds of the early universe that fueled its growth, possibly other black holes that merged with it, an unknown quantity of matter from the galaxy that formed around it. All of that history, all of that physical complexity, all of those structures and processes and events contributed their mass to TON 618, and the object itself carries no record of them. From the outside, TON 618 shows three numbers: the accumulated mass of what may have been billions of years of complex cosmic history, erased into three quantities. The richest, most detailed historical record in the vicinity, the story of the early universe written in falling matter, consumed by the very object whose formation it records, and reduced to three numbers. If the information paradox is real, if information truly is destroyed by black holes, then TON 618 is something specific. It is the largest eraser in the known universe, a 66 billion solar mass region of permanently lost cosmic history. If, on the other hand, the information paradox is resolved by some mechanism that preserves quantum information in Hawking radiation, encoded in the thermal radiation that will slowly leak from the black hole over incomprehensible timescales, then that information exists, but in a form so scrambled and thermally degraded as to be practically irretrievable. Either the history is gone, or it is encoded in a language that humanity has no means of reading. In both cases, the practical result is the same. The inside of TON 618 is where cosmic history goes to disappear. I want to think carefully about something that is often mentioned in discussions of black holes, but rarely examined with the attention it deserves. time dilation, general relativity predicts that time passes more slowly in regions of stronger gravitational potential. This is not a hypothetical effect. It has been measured directly. Clocks at sea level run slightly slower than clocks at high altitude because they are deeper in Earth's gravitational well. GPS satellites require relativistic time corrections to remain accurate. The effect is real and precisely quantified. Near a black hole, time dilation becomes extreme. An observer hovering at a fixed distance just outside the event horizon of a black hole would experience time passing dramatically more slowly relative to a distant observer. For an observer at the event horizon itself, from the perspective of a distant external observer, time would effectively stop. The distant observer would watch the falling object approach the horizon and slow down asymptotically, never quite reaching it, frozen in time at the boundary. The falling observer, from their own perspective, would cross the horizon in finite time. Two perspectives, two experiences of time, both internally consistent within general relativity. For Tuon 618, this time dilation creates an image that I find genuinely disorienting to contemplate. Matter that fell toward Tuon 618 during its active quasar phase, infalling from the accretion disk toward the event horizon, experienced time in a way that diverged dramatically from the experience of distant observers. From the perspective of external observers across the universe, that matter approached the horizon asymptotically, its final moments stretched across potentially billions of years of external time. From the perspective of the matter itself, the crossing was finite and, in the absence of a firewall, possibly almost unremarkable in the immediate geometric sense. Two histories of the same event, two experiences of time that diverge without contradiction. The universe supports both simultaneously. This is not a paradox in the logical sense. General relativity is internally consistent. Both descriptions are correct within their respective reference frames, but it means that the falling of matter into Tuon 2618, the feeding process that built 66 billion solar masses, is an event that looks fundamentally different depending on who is doing the observing and where they are in the gravitational field. There is no single universal description of when the matter crossed the horizon. Time itself does not provide a single answer. That feature of general relativity, the relativity of simultaneity, and the dependence of temporal experience on gravitational position, is one of the deepest and most counterintuitive consequences of Einstein's framework. And TON 618, at the extreme of gravitational physics, is a place where that feature becomes most dramatically relevant. If there is anything near that event horizon, any process, any structure, experiencing time in its own reference frame, it experiences a universe quite different from the one we inhabit. The universe, billions of years older from our external perspective, might correspond to an entirely different duration from the perspective of something in the extreme gravitational vicinity of TON 618. Time itself becomes local, dependent on position, not the universal background that ordinary intuition assumes. In recent years, pulsar timing arrays have detected what appears to be a background hum of gravitational waves permeating the universe, not from a single source. From an accumulated background of many sources, the signal, confirmed by multiple independent research collaborations across different continents, appears consistent with what would be expected from a cosmic population of supermassive black hole binaries, pairs of supermassive black holes in close orbits, gradually spiraling together over millions to billions of years as they radiate gravitational wave energy across the universe. In the centers of galaxies that have undergone mergers, pairs of massive black holes orbit each other, not yet close enough to merge quickly, but close enough to be radiating low-frequency gravitational waves continuously. The combined effect of all of these pairs across the entire observable universe creates a background, a gravitational wave background that pulsar timing arrays can detect as a correlated variation in the arrival times of pulses from millisecond pulsars distributed across the sky. This detection, still being refined and characterized, represents a fundamentally new way of listening to the universe. Not through light, not through radio waves, through ripples in the geometry of space-time itself. And what it hears, what it is beginning to hear, is the gravitational voice of a population of supermassive black holes across cosmic history, including objects in the mass range of 2 on 618. The gravitational wave background carries statistical information about the mass distribution of supermassive black holes across the universe and across cosmic time. As pulsar timing arrays become more sensitive, and as the data accumulates over years, it becomes possible to begin extracting information about that distribution. How many objects of different mass ranges contributed to the background? How the population evolved over time? Whether the early universe contained more extreme objects than current models predict? Whether the anomalies represented by T on 618 and similar objects are statistical outliers or the visible tip of a much larger distribution? The universe is beginning to speak in a new language. We are just starting to learn the alphabet. I want to return to the question of life, but from a different angle than I approached it earlier. Not whether life survives in the immediate vicinity of an active quasar, but whether the existence of ultramassive black holes in galaxies creates long-term environmental conditions that affect the prospects for life across galactic history. The argument goes roughly like this. Quasar activity, while violent, is temporary. The active phase lasts perhaps tens to hundreds of millions of years. After it ends, the galaxy settles. But during the active phase, the intense radiation and jet activity from the central black hole does not simply vanish from the galaxy's history. It leaves consequences. Gas heated by quasar radiation takes time to cool and become available for star formation again. In some cases, quasar feedback may permanently expel significant quantities of gas from the galaxy, reducing the total reservoir available for future star formation. The stellar population that eventually forms in a post-quasar galaxy may be different in composition and distribution from what would have formed in the absence of that violent early phase. The heavy elements available for planet formation depend on how many generations of stars lived and died before the current generation formed. Stars synthesize heavy elements in their interiors and distribute them when they die. The history of star formation in a galaxy determines what raw materials are available for planets. If quasar activity altered that star formation history, it altered the chemistry of subsequent planet formation. For a galaxy that hosted something like Theon 618, the alteration could have been significant. An early period of intense quasar feedback may have suppressed star formation during a critical early epoch, delaying the build-up of stellar populations, and therefore the enrichment of the interstellar medium with heavy elements. A galaxy that might otherwise have been chemically enriched enough for rocky planet formation at a relatively early cosmic age might have been delayed in reaching that state. The planets that eventually formed around stars in that galaxy might have formed later in cosmic history than in galaxies without that violent early phase. Whether they formed at all, whether they formed with the right chemical composition, whether the stars they orbited were stable enough for long-term biological development. All of these questions connect in a real chain of physical causation to the quasar phase driven by the central black hole. Theon 618 may have shaped not just the galaxy around it, but the potential for any life that galaxy might eventually produce. An influence extending not just across space, but across billions of years of subsequent cosmic history. The shadow of a feeding black hole falling across the biological history of an entire galaxy. I want to spend a moment with deep time in a specific way, not the deep time of the universe's past. The deep time of its future. Current understanding of cosmology suggests that the universe will continue expanding, driven by dark energy for the indefinitely long future. The expansion will not reverse into a collapse, at least not given current measurements. Stars will continue forming for perhaps another trillion years, though at steadily declining rates as gas reservoirs deplete. After that, the universe enters what physicists call the degenerate era. Stellar remnants, white dwarfs, neutron stars, and black holes become the dominant objects. Over incomprehensibly long timescales, even those remnants change. White dwarfs cool. Neutron stars possibly decay. The complex atomic structures of ordinary matter may become unstable. And through all of this, black holes persist, growing slowly through the extremely sparse accretion of whatever diffuse matter remains, shrinking extremely slowly through Hawking radiation. The most durable gravitational structures in the universe. The Hawking evaporation times scale for a black hole scales with the cube of its mass. A black hole 10 times more massive takes 1,000 times longer to evaporate. For Theon 6 and 18, at 66 billion solar masses, the Hawking evaporation timescale is so vast that writing it in years requires a number with roughly 99 zeros after it. That number has no emotional meaning, but it can be compared. The current age of the universe is approximately 14 billion years. The evaporation timescale of Tuon 618 exceeds the current age of the universe by a factor so large that the current age of the universe is completely invisible inside it. It will still be there, long after the last ordinary star has died, long after the last white dwarf has cooled to near absolute zero, long after every atomic structure not inside a black hole has decayed. The universe will become a cold, dark, expanding emptiness, populated only by the gravitational monuments of its own history. And Tuon 618, or whatever it has become through mergers and time and accumulation, will be among those final monuments, slowly, infinitesimally slowly, losing mass to Hawking radiation, until eventually, over a time scale that defeats any human attempt at emotional comprehension, it too ends, not with violence. With a final release of radiation, the last photons from a process that began with the consumption of matter in the early universe. A beginning and an ending separated by a duration that makes the entire current history of the cosmos look like a brief opening moment. I want to be precise about what the tension between Tuon 618 and current models actually means for the scientific enterprise. It does not mean physics is wrong. It means physics is incomplete. This is a distinction that matters enormously. A theory that is wrong makes predictions that fail. A theory that is incomplete makes predictions that succeed across a wide range of conditions, but encounter specific situations, instances where the predictions become uncertain, ambiguous, or clearly insufficient. General relativity is not wrong. It is one of the most precisely tested theories in the history of science. Its predictions have been confirmed across an enormous range of conditions, from binary pulsar systems to the bending of light by the sun, to the behavior of GPS satellites, to the detection of gravitational waves. But it is incomplete. It breaks down inside black holes. It breaks down at the Big Bang. It breaks down wherever quantum effects become important at the scale of space-time geometry. These breakdowns are not random failures. They point consistently toward the need for a more complete framework, one that encompasses quantum mechanics and general relativity simultaneously. That describes what happens in regimes where both sets of effects are important. Tuon 618 exists in a regime where the incompleteness of general relativity becomes most directly relevant. The object's formation challenges models built on current physics. The object's interior is a region where current physics breaks down. The object's existence at extreme mass may represent physical conditions that require the more complete theory to fully describe. In this sense, Tuon 618 is not merely an object to be catalogued and filed. It is a signpost. It points toward the places where current physics ends and the next physics must begin. The history of fundamental physics is a history of exactly this pattern, objects and phenomena that did not fit existing frameworks. Anomalies that accumulated until a new theoretical structure was required. The photoelectric effect that pointed toward quantum mechanics. The perihelion precession of Mercury that pointed toward general relativity, the expansion of the universe that pointed toward cosmology beyond static models, the anomalous rotation curves of galaxies that pointed toward dark matter. T-on 618 and its cohort of early massive black holes may be playing a similar role now, not proving that current physics is wrong, but pointing persistently and clearly toward the region where something more is needed, where the next framework will have to account for what the current one cannot. That framework does not yet exist. When it does, T-on 618 will be one of the observational constraints it must satisfy. One of the extreme cases that any genuine theory of the early universe must be able to explain. The universe sets its own exam questions. And the question represented by 2-on 618 has not yet been fully answered. When I think about everything that has accumulated in this reflection, I find myself returning to a single image, a patch of sky, unremarkable to the naked eye, containing within its darkness a faint point of ancient light. Light that began travelling when the universe was 3 billion years old, that crossed the expanding universe for 10.5 billion years. That passed through intergalactic darkness while the sun formed and the earth formed, and life evolved, and civilization built itself, and eventually constructed instruments sensitive enough to catch it. And in that ancient light, when analyzed carefully with those extraordinary instruments, the signatures of something extraordinary, 66 billion solar masses, an interior beyond description, a formation history that challenges our models, a future that outlasts almost everything, a gravitational influence that shaped a galaxy, a radiation output that exceeded entire galaxy populations, a causal region of space-time permanently separated from the rest of the universe. All of that contained in a smear of ancient light, catalogued in 1957, named with a number. The universe does not announce its extremes. It does not label the extraordinary. It does not simplify itself for observers. It contains what it contains. At the scales it operates on, according to the physics it follows, with complete indifference to whether anything ever notices. T-on 618 existed for billions of years before anything capable of noticing existed. It will exist for incomprehensibly longer after the last instruments capable of noticing have ceased to function. The brief window during which humanity collected its ancient light and attempted to understand what it implied is a moment so small against the object's total duration that it barely registers. And yet it is the only window we have, the only moment of contact between this extraordinary object and conscious curiosity. What we have learned in that moment is significant. What we do not understand is larger. And what we cannot ever know, what the interior holds, what it truly is, what it has become in the time, since those photons departed, is larger still. The universe remains mostly unseen, not because it hides itself, but because it is very large, very old, and very strange. And we are very new. Tone 618 was already ancient before the Earth formed. It will still be present when the last star in the Milky Way exhausts its fuel, and in the immense darkness of deep time, When the universe has expanded and cooled and emptied itself of almost everything familiar, the gravitational monument of 66 billion solar masses will continue dark, unaware of being watched, indifferent to being understood. The last kind of thing left in a universe that has outlived almost everything it once contained, waiting with complete unconscious permanence for a physics we have not yet written.